All right. So welcome to the new people that joined us at the ORC IAP seminar. Thank you again to Negin for her talk. It is my pleasure to introduce you to our second speaker today, Nathan Kallus. So Nathan is an assistant professor at the School of Operations Research and Information Engineering and Cornell Tech at Cornell University. His research evolves around data-driven decision-making, around the interplays between optimization and statistics for decision-making and inference, and the analytical capacities and challenges from observational data. Nathan holds a PhD from MIT in operations research, which is a wonderful program that you all know about. Also, a Bachelor of Arts in Mathematics and Bachelor of Science in Computer Science from Berkeley. Before coming to Cornell, Nathan was a visiting scholar at USC in the Department of Data Science and Operations, and an associate postdoctoral at the MIT Operations Research and Statistics Group. Thank you, Nathan, for coming and presenting you your work.
Thanks so much. Thanks so much for the introduction. Thanks so much for the invitation and for organizing this. It's a real pleasure and an honor to be here. The theme of my talk today is decision-making in the presence of unobserved confounders. It's based on work that's joint with my student Angela. A preliminary version just appeared in NeurIPS last year, and a journal version is under revision right now. And although I'll be focusing on just this paper with Angela, I'll also be mentioning some other work coming out of my lab. So I want to use this opportunity to thank not just Angela, but all the amazing members of my group. This work would not have been possible without them. OK, so to motivate the problem that I'm going to be talking about, I want you to consider the following scenario. Suppose patient Anna has just arrived in your hospital, and she's been diagnosed with type 2 diabetes. By looking at her records, you can see what her blood sugar is right now, what it was, her age, her weight, BMI, et cetera. And you collate all these into some feature vector x, which we're going to call the baseline covariates. And the question is, given what we know about Anna at this point, these baseline covariates x that characterize her, what should be the first-line glucose control treatment that we should give her to manage her newly diagnosed diabetes? And we'll simplify the problem and just focus on two alternative treatments, and suppose that we're just going to look at pharmacological regimens. And we ask the question, should we treat her with insulin encoded by t equals +1 or metformin encoded by t equals -1? And of particular interest, in order to answer this question, is what is the causal effect of giving one treatment versus the other, okay, on a particular outcome of interest? And more generally, what we want is a policy that would tell us what to do when generally encountering an individual with a particular set of features. What should be the treatment that we should give them that would be best for them individually? Okay? And you can pose the same question in a lot of other application domains, not just precision medicine. So if we want this policy, we should need to learn it from some data. And so what data is out there from which we can learn this policy? Well, luckily, this hospital that Anna has arrived at has a very large electronic medical records, or EMR, database. So the hope is maybe we can pore through this database, find all the diabetic patients in that database, find out what their covariates were at the time that they were first diagnosed and treated, record them, record what that treatment was, and record an outcome. Maybe this is blood glucose over time after the treatment. Okay? And then the hope is to use this data to learn what should we do to treat Anna, and how should we treat people like Anna? And so this procedure of going from data on features, also known as states or covariates, and actions and outcomes, to a policy is known as policy learning. And how might we do this maybe in this particular setting? One simple approach would be as follows. We could take all the individuals over here who've been treated by metformin, look at their covariates, and look at their outcomes, and build a predictive model, a machine learning model, that would, given a covariate x, predict what that outcome is. Okay? And that's illustrated here by this blue curve. And obviously, x is very, very high dimensional. I'm just visualizing here it with one dimension. We could do the same thing exactly for all the patients with insulin. And then when a new patient comes in and has a particular set of covariates, say Anna, we can predict what their outcome would be under the two treatments and see which one we think would be better. Right? And we would identify this difference as our best prediction for the causal effect. But the problem with doing this is when we're dealing with EMR data is that we might have to contend with an issue known as confounding. For all we know, these individuals in this population segment over here who got metformin, maybe they were healthy to begin with, right? Maybe the people who got insulin were worse off to begin with. And maybe this difference is not indicative of some causal effect of metformin versus insulin, but rather just a matter of fact about these two different populations, right? So that issue is known as confounding. But there's another alternative reason that would explain an observed difference. And the issue here is that if we were to follow the recommendations by this procedure, we might intervene when it's not really necessary, because we see an effect that's not really there. Okay? So how do we usually deal with issues of confounding? Well, the standard thing to do is to run an experiment, right? Randomize individuals into drug A or drug B. And if we randomize them, then there should be no reason why their underlying healthfulness should correlate with what treatment they got, because we randomized it. So that's what's nice about experimental data, but the problem is that it's going to be necessarily small scale. It's going to be poor in covariates, and most of the time we don't have the experiment that we want. We don't have an experiment run in the hospital that Anna went to. Maybe we have an experiment that was done in Germany, and we don't even know if the results generalize to this population. So we don't even know if it can be used for this. Okay? It definitely can't be used for fine-grained individual treatment determination. On the other hand, we have observational data. Observational data is very rich, it's very plentiful, but it's going to be confounded. And it's always going to be confounded because we give treatments for a reason, not at random, right? So it's a complete opposite situation. And so just to drive this point home that making decisions based on confounded observational data is problematic, I want to show some bad examples of bad decisions that were made based on biased observational data. And maybe the most prominent example that comes to mind is that of hormone replacement therapy, which was thought to be a safe treatment for the vasomotor symptoms of menopause, okay, stuff like hot flashes. And the fact that it was safe was actually based on some observational evidence. So this drug Premarin, which is an estrogen replacement, which has a lot of other uses, was being used to treating menopause in 2001. It was, in fact, the third most prescribed drug in the US. But just a year later, a clinical trial known as the Women's Health Initiative, looking at the use of hormone replacement therapy for menopause, had to be terminated early because the treatment arm had a much increased rate of coronary heart disease, cancer, and other bad outcomes. So that immediately led to an 80% reduction in the prescription of Premarin, and to a big debate about observational evidence versus clinical trial evidence. And if we look back at the data and we ask, well, what happened? We see a lot of causes for confounding. Two prominent one is what's known as healthy user bias. These people who are seeking treatment also had other health-seeking behaviors like exercise, which correlated with good heart health, and hid this extra risk of CHD. Same time, we had confounding by indication. The individuals who were seeking treatment also had worse off vasomotor symptoms to begin with. There's a lot of other examples in public health and in advertising. In advertising too, we see a big difference between the causal effect of advertising as would be measured in observational data versus as it would be measured in experiments, has been documented by this famous study by Lewis et al. And the examples continue. There's probably one in your favorite application domain too. It's very dangerous to observational data. So let's go back to the question of policy learning, where we're interested in individual level causal effects, right? And if you thought that confounding was an issue in the aggregate levels, right? We're not sure if HRT is really causing coronary heart disease or not on average. This issue is going to be even more insidious, even more latent when we're talking about fine-grained individual effects. And the problem is that the current approaches for policy learning, including a lot of my own work, assume an assumption known as unconfoundedness. So they rely on this assumption, which says the following. There could be variables, confounding variables, that correlate who got what treatment and what is their underlying outcome idiosyncrasies, like underlying healthfulness. But we've observed all of them. To the extent that they exist, we've observed them. So another way of stating this, there are no unobserved confounders. And how would you defend such an assumption? The way you defend is you would say, look, I have very, very rich EMRs. I have so many variables. I've controlled for all of them. How could it ever be that there was something I didn't control for? You know, I have so many columns in my table. But of course, that is a flawed argument. There's always going to be some factor you haven't accounted for. And just observing a true confounder with noise is a form of confounding. So again, by default, in any situation where you're dealing with observational data, there's definitely going to be some sort of residual confounding by default. Completely unavoidable. And whether it's true or not that you have a confoundness is fundamentally unverifiable because it's concerning the presence of something you've not observed. So how could you tell whether it exists or not just from the things you've observed? Okay, so it's always going to be there, latent, and causing problems. And one of the problems it's going to cause is this problem of unidentifiability. So what does that mean? It means that just by looking at the data, I can't distinguish from the reality where HRT really causes coronary heart disease and where it doesn't cause coronary heart disease. Those two situations are indistinguishable just by looking at the data itself. And therefore, the causal effect, whether it's 0 or non-zero, is not identifiable. Yeah, Negan?
Verifiable, because imagine that I'm running a regression, just simply linear regression.
Yeah.
And then I get some residual, so I can see that this residual is going to be independent from the other.
The residuals are always going to be independent just because you're projecting. So this is actually a different. So let me come back to that when I set it up and try to draw the contrast between regression errors being independent and what this independence means. Okay? But I think let me answer your question this way. Suppose I have no covariates. Okay? The residuals will always necessarily be independent, right? Because y minus its average mu is uncorrelated with y itself by definition, by construction. Right? That has to be uncorrelated if I've subtracted the mean. But if I look at all the people who've say smoked and they have cancer, so I see once I subtract this mean, it's uncorrelated. That doesn't mean that necessarily smoke can cause cancer. It doesn't mean that there's no underlying cause. So we're going to need to develop a notation for these counterfactuals in order to understand what does that mean. So. Yeah, so endogeneity, you cannot test for it unless you have some sort of, you know all the confounders, you have some other identification scheme, such as an instrumental variable, such as a front door, and those would themselves rely on some unverifiable assumptions that cannot be determined just by looking at the observed data. So the situation would be the same. Okay. And so that's a really, really great question. Okay. So the issue here is that if we're going to use methods that assume unconfoundedness when unconfoundedness doesn't really hold, the concern is that we're going to find effects that are not really there. And then we might seek to intervene when it's not actually necessary. And if you think about this as a whole process of coming into an application domain, saying, you know, I'm a data analyst, give me your data, I'll crunch it, and I'll give you a policy, and you should forget what you're doing now, and you should do this now. That whole process actually could potentially introduce net harm rather than net good. So why should anybody trust you, right? So hopefully at this point, I've convinced you that using observational data is really, really dangerous, and you shouldn't do it. You shouldn't just use assume unconfoundedness when it's false, right? Of course.
So suppose one argue the following, that we use observational data to create projection, not verify. I agree on the
Absolutely.
To create
which you then would test with a trial.
And then you randomly test,
yes.
the same testing the algorithm.
Yep.
And then you observe, that would be sort of defining the algorithm.
That would be a better thing to do than what they did with HRT. What they did with hormone replacement therapy, where they just gave it to all these women. Right. Absolutely. Yeah, so that's another alternative.
I view the inference from observational data, because in the end, whatever method we use, all of the criticism will be there.
Absolutely. So how do we... We're on the same page, exactly, right? And the question is it doomed, or should we just use it to pose conjectures and actually not use it as evidence to make decisions?
Finally.
Yeah. And what I'm going to argue is that, no, actually we can still use it to make decisions in a safe way. All we have to do is focus on well-evidenced improvement and on robust improvement that would improve on standards of care no matter what the confounding is. Okay? Instead of trying to focus on efficiency, focus on robustness. So how am I going to do that? Quick overview of what I'm going to do. So I'm going to seek to develop a framework for safe decision-making in the presence of unobserved confounders. And the approach I'm going to take is I'm going to take this work of policy learning, which I've done a lot of work in that space, and I'm going to try and calibrate these methods to realistic violations of unconfoundedness, right? Situations where there could still be some residual confounding. And the approach is going to be pretty simple. I'm going to find policies that are going to minimize over a class of policies the worst case regret relative to the current standard of care. Okay? So I'm going to look at what is my regret relative to what people are doing right now. If it's positive, I've introduced harm. I regret this decision. Okay? So I want to have the regret I want to bound the regret, make sure it's negative. So I'm going to minimize the worst case regret. Okay? And there's two important components to this approach. One is what does worst case mean? And two is how I'm going to estimate worst case regret. So for defining worst case, what I'm going to do is I'm going to use a tool from causal inference known as sensitivity analysis to construct, in some sense, an uncertainty set for the confounding. And then I'm going to develop what I'm going to call the minimax Hájek regret estimator to estimate this worst case regret, so I can minimize this estimator. And I'm going to show something that is known as uniform sharpness, which is going to lead to the following improvement guarantee immediately. I'm going to be able to show that we're going to be guaranteed that almost never will do worse than the baseline. And we may do better, and we can check this by just looking at the objective value of this program that you're optimizing. Okay? And so we'll talk about the exact conditions under which this would hold. But this essentially underlies the appeal of this method, how you can have reliable policy learning from observational data. Right? You have a guarantee that you're not going to introduce harm. And I'm going to try and showcase the safety of this method versus the danger of assuming unconfoundedness when it doesn't hold in a particular example for the treatment of ischemic stroke. Okay? And that's where I'm going to end. Okay, so next what I want to do is I want to set up the problem, define some notation, define exactly what we're looking at, and do a quick review of what can you do when you do have unconfoundedness? What kind of policy learning methods exist currently? Okay, so the setting goes as follows. We're going to look at a simple setting of just two treatments. So we're going to have two treatment options, +1 and -1. Usually you're going to think about +1 as the more invasive, more intense, more active treatment. -1, the less invasive, less intense, more passive treatment. And each one of these treatment options is going to be associated with two variables. So if we think about that person, Anna, there's two variables associated with her. The outcome she would experience if she were treated with treatment -1, and the outcome she would experience if she were treated with treatment +1. And the convention I'm going to use is that we want smaller outcomes, so we can think about these as the disutility that Anna experiences. Okay? But these just exist hypothetically. We can't observe these counterfactuals simultaneously. Instead, what we observe are the following. We observe in the observational data the features of each individual. We observe the treatment that the individual was treated with and the outcome. And the outcome that we observe, Y, is the potential outcome that corresponds to the treatment with which they were treated. What we never observe is the outcome of the treatment that they weren't treated with, this counterfactual. And that will always remain an unobserved confounding. And another name for this phenomenon where things we don't observe, we can't observe, in this situation is known as the fundamental problem of causal inference. I don't know what could have been. Okay? And the way it's usually dealt with is by making this assumption, unconfoundedness, which in this notation would, to its own peril, assume that the potential outcomes, which here constitute this underlying outcome idiosyncrasies, like underlying healthfulness, are independent of treatment assignments once we condition on X. So once I condition on you being a student, being young, I no longer have that knowing which treatment group you are assigned to gives me information about your underlying healthfulness. I've already controlled for that. Okay, so that's what unconfoundedness assumes here. But as I've been saying already, we're not going to assume this in this talk, okay? So we're not assuming this, but this is what we would assume if we had unconfoundedness. A policy is going to be a map from covariates to the probability of being treated with treatment +1. The risk of a policy, the way we're going to measure what's a good policy or a bad policy, is going to be the average outcome it induces in the population. Okay, so if we see somebody with features X, we give treatment +1 with probability pi of X, which has outcome Y of 1. We give treatment -1 with probability 1 minus pi of x. Okay, so this denotes the overall outcome, average outcome that we would get if we always follow policy pi. And then I'm going to find regret simply as the difference of the risk of some policy pi minus the risk of some other policy pi naught. And usually I'm going to think about pi naught as whatever is currently being done, whatever is the standard practice, because I want to make sure I have no regret relative to pi naught. Okay? So this is a different definition of regret. It's not as sometimes is defined. It's not relative to the optimal. It's relative to the current standard of care. And the learning task is simply train a policy based on observations of features, treatment, outcomes. So if you did have unconfoundedness, what could you do? So one thing you could do, which I alluded to already in the first slide, is use an approach based on learning the conditional average treatment effect, or CATE. Okay? This function is the average effect, difference between the potential outcomes, in a particular population segment of x. Right? So the conditional expectation of the difference given x. In some sense, this is the best prediction for the difference if all I see is x. Under unconfoundedness, which I've marked by star here, I can rewrite this as the difference of two regressions. The regression of outcome on features in the treatment +1 population, and the regression of outcomes on feature in the treatment equals -1 population. Okay, so this is exactly what we did in the beginning. We said, oh, let's create a predictive model in the metformin group. Let's create a predictive model in the insulin group and look at that difference. Under unconfoundedness, that would give us the CATE. So all we have to do is fit this difference and compare it to 0. When the difference is positive, one treatment is better. When it's negative, the other treatment is better. There's also a variety of methods which, under unconfoundedness, would learn this difference directly rather than learning the regression functions separately. Another line of approach we could take is based on something known as inverse probability weighting, which would go as follows. We define E tilde T of x as the probability of being treated with treatment T given that your features are x. Okay? This is known as the propensity score. Then we can use it as follows. Suppose we want to evaluate that first term in the risk of a policy, right? The expectation of pi times y of 1. That was that first term. We can rewrite that in the following way. On the left here, we have an average over the whole population of some outcome y of 1, which we don't know about everybody. We can replace that with an expectation only over the t equals 1 population. Okay? In the t equals 1 population, the outcome that we see is, in fact, the outcome of treatment 1. All we have to do is reweight this population so that it looks like the general population, which amounts to just reweighting by the inverse propensity score. Okay? So these two things would be equal if we had unconfoundedness. We can apply this to every part of the regret, combine it with some algebra, and we would arrive at this following reformulation for the regret of policy pi versus pi naught. So whereas this quantity had a lot of y1s, y minus 1s in it, this quantity only has observable quantities, x's, t's, and y's. Yeah?
Is there an assumption on the balance of the covariance?
So in some sense, balance is assuming that this thing is bounded between 0 and 1, so we can divide it by it. Yeah, great question. So this reformulation would then suggest the following approach. We have this expectation, replace it with an empirical expectation over your data. Right? Just replace each of the x by xi's, t by ti, y by yi, take a sum, and then minimize this estimate for the regret over some candidates for policies. Okay? Let's call it cap pi. And this approach is very, very popular. It's appeared a lot in my own work, in some work in CS, in work in econometrics, in work in biostatistics. Just goes to show why it's a good idea. It's appeared in a lot of places. And one thing I would note here is changing what pi naught here doesn't change what the optimal policy pi here is. OK, I'll just quickly note some notable extensions to this approach. You can get what's known as W-robust policy learning. If you replace this IPW objective with something known as the augmented IPW objective. I won't get into the details, but that's something that's been seeing a lot of attention recently. Something that I've looked at is here you're dividing by probabilities. So you're dividing by things that could be close to 0. That is extremely unstable and can actually lead to bad policy learning, even under unconfoundedness. So I've looked instead at how to use optimal balancing, where we optimize the error instead of just plugging in estimates. I've looked at how to learn tree or forest or optimal tree policies in this kind of situation. And I've looked at how to handle continuous treatments. This derivation relied very strongly on there being just 2 treatments. So it's a question what to do when you have continuous treatments. But if you have confounding, as you will necessarily have in any situation with observational data, well, the risk of a policy is an unidentifiable quantity, just like the causal effect is not identifiable. So no matter what fancy machine learning you're going to do, you just can't get at that number. It's not knowable. Right? So all of these methods might actually introduce harm. They're all subject to that critique we had before. Some other work that I've done has looked at how to handle latent confounding in different situations, not policy learning. So one thing you can do is if you have high-dimensional, noisy, and missing views on the confounders, we show you can use matrix completion to still identify causal effects and give finite-sample bounds on how big the error can be. I've also looked at how to use, if you have a small experimental data set that could even be, that data set in Germany that doesn't generalize to us, you can actually still use that to deconfound your Kate estimates from a large observational data set. And when we have confounding this Kate function, it's not point identified, right? Just like the causal effect, there's no one point. But instead, you can say there's an interval of things it could be. So if you're interested in individual level effects, what you're interested in is in an interval valued function, which for each person will give me an interval of the causal effects it could have. Okay, so then the question is, how do you learn such an interval valued function? And that's something that we've looked at as well. But what I want to talk about is, what do we do for policy learning? How do we learn the best policy, or how do we learn a good policy in a situation where we can't identify any causal effects? Okay, so let me tell you a little bit about our framework and how we actually do this. So the first thing we're going to do is I'm going to construct this Hájek estimate that I've alluded to before. Without loss of generality, we can think about there being some additional variable u, which is unobserved, which if we did observe it and controlled for it in addition to x, we would have unconfoundedness. Okay, so you can think about u as being the potential outcome itself. It doesn't really matter what you use for u. It's just there to kind of simplify the exposition. Okay, so there's some u. You can think about u as being the potential outcome itself, the underlying healthfulness itself. Okay. If we did have u, then we can construct the true propensity score when we control for x and u. And we'd be back in unconfoundedness land, and everything would be fantastic. We can form this true IPW objective, which would be in terms of the inverse propensities. Let's call these things W star, and do the same thing as we did before. Yeah?
I mean, even if you were observed, we still wouldn't have a true propensity score typically.
That's correct. You'd still have to estimate it. Yeah? But it would be an object that exists. Yeah, but that's a fantastic point. Yeah. Right? We might not actually know it. We might need to estimate it from the data. But the good thing about propensity scores is that they are identifiable. They only involve observable quantities. OK. We could actually go further than just forming this true IPW objective. We can note that the expectation of W star, if you work out the algebra, it's always going to be 2 no matter what. So we can actually use this as a control variable and normalize our IPW objective by it. Okay, that would give rise to the following Hájek estimator for the regret. We took the thing we had before. We put it times 2 in front, and we divide by the sum of weights. Okay? And the reason I'm calling it Hájek estimator because any estimator that has the form of a weighted sum divided by the sum of weights, that thing is called a Hájek estimator. Okay? So it's a Hájek estimator for the regret. And by putting a pi naught here and dividing by w's, I haven't really changed what pi optimizes this. So I haven't really done anything yet. Okay? This is just a constant scale and shift relative to pi. As David was saying, this true propensity function is unknown. Right? That's the problem. That's why we're stuck. So what I'm going to do is instead I'm going to put some bounds in it and assume something about it. Okay? In particular, what I'm going to assume is going to assume that the log odds for treatment between if I control for x, the observed variables x, or whether I control for observed variables x and unobservable variables u, that odds ratio is going to be bounded by some number gamma, okay? Bigger than or equal to 1. If gamma is 1, that is like assuming unconfoundedness. Okay? As gamma increases, we allow bigger and bigger deviations from unconfoundedness. So where does this thing even originate from? This is actually coming from an idea called the marginal sensitivity model, which originates in the following thought experiment. So we see that smokers have more cancer. Does that mean that smoking causes cancer? Or could there be an alternative reason? Something at the time was called hormone X, which is causing people's both lust for nicotine and a susceptibility to cancer. Okay, so Kornfield et al. in 59 tried to think about, well, let's think about that. Let's push that idea and think, what does that kind of imply if that were the case? If cigarette smokers' increased risk for lung cancer is due only to this hormone X confounder, then it must be that this never before seen, explained, or studied entity has to be 9 times more prevalent in the smoking population. And if this proposition is as implausible as it sounds, then smoking must cause cancer. Okay, so here this gamma would be 9. And so this marginal sensitivity model has seen a lot of use in causal inference, where there's been a lot of proposals on how to calibrate gamma using negative controls. You see an effect that you know must be 0, so you ask how big should gamma be to invalidate that, and comparing what would happen if I let xu be my whole x and drop covariates, what gamma would that induce? And think, do I think of something as big as gender? Yes?
Where's the number 9 coming from?
Where is what?
Where's the number 9 coming from in Kornfield?
9? So Kornfield was asking how big does gamma have to be in order for the partial identification interval and the effect of smoking to include 0. Sorry, to not include 0.
Is it not making any assumption on the form of the propensities?
No, just this. Yeah, so another way to think about it is take logs, okay? So this would be the same thing as saying that the absolute value of the logit, okay, so the logit is the log of p over 1 minus p. So the logit of e plus 1 of x minus the logit of e plus 1 of x and u, absolute values of that is bounded by log gamma. Okay, so one way to think about it is, suppose you have an additive logit model, then there's like a bounded interaction with u. There's one way to think about it, but it's more general than that. But that's kind of where it's coming from. Okay, so if we are just, so there's a few ways to calibrate gamma. In the end, I'm actually going to talk about a data-driven way to do it, because here we're actually dealing with an objective value and a decision. But let's just take this model to be true for now. And if you do some algebra, you can see that it immediately implies an uncertainty set for these true weights W star, the weights that we would have wanted to put into our IPW objective. Okay, and so massaging this formula gives us this uncertainty set for W star, which is somehow centered around these fake inverse propensities, right? The inverse propensities that only control for X, the fake ones. So we get this box uncertainty set. So what I'm going to do is pretty straightforward. I'm going to say, let's take that Hájek estimator I had before and say, well, I don't know what W star is. Let's take the worst case over this uncertainty set. Okay? And I'm going to find this R bar. Okay? This is the worst case Hájek estimate of regret. And what I'm going to do is I'm just going to play a game, pi versus W. I'm going to try and minimize this ratio, and W is going to try and maximize this ratio. By doing that, what I get is I get the policy in some candidate set of policy, cap pi, that minimize the worst case regret. Okay? So the candidate set of policies can, for example, be hyperplane policies, right? So if I can choose some hyperplane and choose to treat on one side, not to treat on the other side. It could be trees. We'll see examples of different policy classes later on. Okay, so this is the approach, pretty straightforward. And now that I've actually put a soup W here, now the fact that I've centered at pi naught and divided by the sum of W's actually does affect the structure of the solution, right? Actually, dividing by the sum of W's is going to be key to this sharpness, right? That this worst case regret actually converges to the worst case it could be. And centering around pi naught says, well, it emphasizes improvement over particular baselines. If the W player is completely unrestricted, right, then I'm afraid that this ratio could be positive, but I can always make it 0 if I play pi naught. If I pay pi naught, my regret is 0. Okay? So that really changes what the solution is, choosing what pi naught to put here. Okay, so I've now, so there's other ways to construct the uncertainty set. I won't talk about this alternative approach, but generally the procedure is generic, right? It's for any uncertainty set. Here I've proposed one way to devise the uncertainty set. So I've described what the approach is, I've defined it, but I haven't told you yet what I can say about it. Is it good, is it bad, and how do I actually solve it? Okay, so how to actually solve it is the question of algorithmically, how do I learn these policies? But for now, let me talk about, having defined what pi bar is, what can I say about it? Is it good or is it bad? So we prove in the paper the following theorem. This says that suppose that the outcomes are sub-Gaussian, that is, they have nice tails. They don't have fat tails. They have small tails, or if you want to think about it, just think about bounded outcomes. That would be sub-Gaussian. And if the set of candidate policies has a finite VC dimension, okay, so if you're not familiar with VC dimension, examples of such policy classes would be hyperplanes, as I've mentioned before. You choose some hyperplane, treat on one side, don't treat on the other side. If-then rule lists, constraint scorecards, or decision trees are all examples of policy classes with finite VC dimension. If the true propensity is bounded, then I have that with high probability, the true regret of any policy pi is bounded by the worst case Hájek estimate of the regret plus some term that looks like 1 over square root n and has sub-exponential tails. So sub-Gaussian tails would be like a square root on the log, but this is sub-exponential. And this happens uniformly over all policies in pi. In particular, it would hold if I minimize this right-hand side. Right? And the pi that minimizes this right-hand side is pi bar. Okay, so let me summarize this theorem just by saying, let pi bar be the pi bar that we chose, the one that minimizes the worst case regret. Then the true regret of this policy pi bar relative to pi naught is bounded by the worst case regret, right? This is actually the value of the game that we're playing. That's the value of the min-max game that pi is playing against w, plus some OP of 1 over square root n term with sub-exponential tails. Of course. So gamma, so this I'm talking about generically about uncertainty sets w. So gamma will need to be well specified. So I need to have that my sensitivity model is well specified, right? So it's true. Saying that a particular gamma holds is itself an unidentifiable, right, unverifiable assumption, but it's weaker than unconfoundedness. So how to choose gamma is something I'll get to at the end. But this assumption over here is essentially saying that gamma is well specified. It says it's over here. It essentially says that gamma is well specified. The W star is really satisfying this sensitivity model that we've specified.
It doesn't need to show up in the bound because
it's in here. Gamma is in here.
I see what it is. Approximately, I understand.
Okay.
Exactly.
Okay. I'm happy to explain more later. Okay. So we get this guarantee about the pi bar policy that we chose. And we show that the regret is bounded like this. And let me explain why this really captures the special appeal of this approach for policy learning from observational data. As long as we put pi naught in our set of candidate policies cap pi, which is our choice, we chose what cap pi is, just put pi naught in there, then we can always play pi naught. Playing pi naught guarantees zero regret. That means that the value of the game has to be non-positive, because we can only do better than that. Okay? So that means that this number is non-positive, which bounds the regret, almost up to some fudge factor. So we're almost always assured not to introduce harm. Okay? If we check the value of the game and we see that it's in negative, then we're almost assured some improvement. Okay? So that gives us this guarantee, the certificate on the regret of this policy. So since I've been taking questions, meanwhile, as Nicholas was suggesting, I'll just go for and allow maybe some 7 minutes at the end for questions, okay? And so I'll have some time to talk a little bit about the algorithmic approach, but I'll go quickly through that just so I can have some time to talk about the empirical results. So the question next is, how do I actually implement this algorithmically? I've described what this pi bar is, but how do I find it? So essentially what I want to do is I want to solve this game, pi versus w of this objective, okay? So let's first talk about this inner problem, right? This thing I called R bar before. On the face of it, it doesn't look convex. There's a division by sum of w's, but I think people here have all taken optimization methods or intro to linear programming and might recognize this as a fractional linear program, except that u might not be linear, okay? But we can still apply what's known as the Charnes-Cooper transformation, which would give us the following reformulation of R bar as a convex program over this cone of u of a linear objective in W. So what this means is that if the uncertainty set is a box, you can use LP duality to get an efficient solution to this. You can find the worst case W just by sorting. Okay, so that's an n log n algorithm. Generally, if you use something else, just send it to some solver. Okay? So we can use these in two separate scenarios, and I'll just give an overview of this instead of going into the details. One setting is if you have a policy class that is parametric and differentiable with respect to the parameter, and then the algorithm would be use online gradient descent to play this zero-sum game. All you have to do is at each step solve for W, but that's exactly what we did before. Okay? So I'm going to use this in the empirics to train this confounding-robust logic policy, okay, which has this structure. So I'm just going to learn this data. We might also want an interpretable model, like a tree, like in the case that I was talking about before. Well, in interpretable regression classification, the approach is usually, let's model this as some MILP and optimize it, right? Like in optimal trees or in optimal decision rules. So we have some classifier, and the way we optimize it was we just restrict the values that the classifier can take on the training data to be in some set, and we formulate that as some MILP. So we can embed this into policy learning as well, into our objective, using the following reformulation of the problem. We just hand it off to Groovy. So in the empirics, I'm going to use this to train what I'm going to call the optimal confounding-robust tree. OK. So what I want to talk about next is, well, how does this actually do in practice? And I'm going to skip the synthetic example and skip directly to the clinical example. So what we did here is we looked at the setting of trying to treat ischemic stroke. Okay? And ischemic stroke is the most common type of stroke. It's the stroke that's caused when the arteries to the brain are narrowed or blocked. And it's often treated by giving blood thinners or anticoagulants. So this trial was looking at the use of aspirin and or heparin, which is another blood thinner. And we're just going to look at two arms from this trial. The aspirin arm, which is a less intensive treatment, and the aspirin plus a high dose of heparin arm, which is a more intensive treatment. Okay? And we have 7,000 patients, and 1/3 of them have been treated with heparin. I'm going to... Yeah, so they arrived with a stroke, with an acute stroke, and they had to be treated right away. Exactly, yeah. OK, so we're going to look at an outcome that's going to measure a variety of things. It's a composite score. It's going to measure whether somebody died or not later on, whether they have complications, a recurrent stroke or other complications, such as hemorrhaging, recovery time, et cetera. And we're going to put all that into one composite score that summarizes those things. We're going to take these 7,000 patients, and we're going to randomly split them into a training set and a test set. The test set we're going to leave as is, as a randomized trial, so we can do some out-of-sample, unbiased, out-of-sample evaluation. The training set, we're going to come in and try to introduce some confounding in there to simulate this issue. OK, so the way I'm going to do this, I'm going to take the treatment arm and remove the units in it with the 10% worst outcomes. I'm going to look in the control arm, and I'm going to remove the units with the 10% best outcomes. Okay, so it's essentially removing people based on their underlying healthfulness. So if you look at the IST data before we did all of this, the average treatment effect of giving aspirin versus giving aspirin heparin was 0.14 in this composite score, which is a significant outcome in favor of aspirin. Indeed, the conclusion of the IST study was we should just give aspirin to everybody. Don't use heparin. That was the conclusion. Okay? If you apply this funny censoring, which is going to make heparin look better than it really is, you flip this to a significant negative 0.29. OK, so on this training data, we're going to train a variety of policies. And these are going to use the following 28 covariates. These covariates are going to be based on age, indicators of conscious state, biological sex, blood pressure, and all sorts of assessments like, is there a facial muscle deficit in the patient? OK, so these are things noted by the physicians. Out of sample, we're going to use unbiased evaluation using the randomized data. OK, so the results look like this. And let me explain to you what we're looking at. So let's look at the top plot first. What I'm plotting here is the policy regret, the true policy regret, relative to control, where control is always give aspirin. These blue and green lines at the top are two methods that you might apply if you assume unconfoundedness. One is IPW, just vanilla IPW. Another is try to learn the Kate using a method known as causal forest and compare the estimate to 0. Okay? Both of these approaches have positive regret. They introduce significant harm into the system relative to just doing what IST recommends to do. Okay? these lines over here, these denote various variants of our method as we vary the gamma parameter in our approach. Okay? So here is the gamma. On the very left, we have log gamma equals 0 or gamma equals 1. We're essentially assuming unconfoundedness, and we're doing the same thing, also introducing harm. Okay? As we increase gamma, we say focus on more well-evidenced improvement, be careful in who you're treating, and we're able to achieve negative regret. Okay? So we're achieving some improvement. As gamma increases further, we're really afraid of intervening because we don't know what might happen. If there's a lot of confounding, the data says nothing about what the real causal effects are, and we default to just giving pi naught, okay, and getting 0 regret. In brown is in red is the logic policy. In purple is the logic policy with the alternative uncertainty set. And in brown is an optimal tree of depth 2. And what's notable here about the optimal tree is that it's just depth 2. It's just making 2 queries about covariates. It's a very, very simple interpretable model, and it still has comparable competitive performance. So negative regret is a good thing here. Negative regret means that I've improved on pi naught. Yeah, but the benchmark isn't the optimal. The benchmark is what's being done right now. So you're asking, relative to what's right now, do I regret what I've done? That would be positive regret. Or do I think I've done something good? That would be negative regret. Exactly, yeah. It's with respect to control, which is here, give aspirin to everybody. Okay, the optimal thing is actually some personalized procedure. So what we see is as we increased gamma, we indeed treat fewer and fewer patients. Right? We give aspirin to more patients and heparin to fewer patients. This is what this plot is showing. And then the question is, well, who are these individuals over here that we're just focusing on giving heparin to in order to get this negative regret? And if you look into the data, what you find is that the patients that we're treating are exactly the ones with the worse off prognoses, which could actually stand to benefit from a more intense treatment. Okay? So that would make sense where we would see this benefit. Now here, what I've done is I've simulated this. Or I didn't simulate this, but I should say I've tested this out of sample for a variety of gammas. So this is not something you could do in practice. You couldn't actually in practice use this to choose gamma. You would have need for gamma to be well specified to begin with. So you could choose gamma based on negative controls, such as this idea from Cornfield, like how big does gamma have to be to invalidate a causal effect I know it's not there? Or say I drop variables, it induces a particular gamma, and I say, well, dropping gender causes a gamma of 2. Do I think I've dropped something as a variable as important as gender? If not, then gamma must be smaller than 2. So those are the kind of approaches you can take. But really here, we can take a more data-driven approach to choosing gamma. And this is the procedure that we recommend. So let me explain to you what this plot is showing. In different colors, we have different variants of our policy as we vary gamma. When log gamma equals 0, gamma equals 1, we're essentially doing the IPW policy. Okay? And the line shows for each value of gamma naught, what would be the worst case regret relative to control if confounding could be as big as gamma naught. Okay? So over here on the left, we're saying there is no confounding. And in the world where there is no confounding, IPW is king and gets the lowest regret. But just under mild violations of unconfoundedness, IPW could actually introduce harm. Okay? So we're worried about implementing it. These blue notches over here denote the omitted variable bias of omitting each one of the variables that we have in the data set. So it says maybe you should worry about gammas in this range. So if you worry about these kind of gammas, you would say, I'm worried about implementing IPW. It might introduce harm. Alternatively, you could choose this purple policy over here. This purple policy would be sure to not introduce harm in these kind of scenarios. And if unconfoundedness really, really holds, or almost holds, we wouldn't be giving up too much efficiency relative to IPW. And if there's some violations, we'll actually be doing better than IPW. Okay? So you can actually make this plot and judge how much confounding you're worried about in order to decide what should your gamma be. Okay? And I won't go through this. It's just making the point that we're not harming any one subpopulation in order to make the overall regret negative. Okay, so let me just recap what we talked about here. My aim was to develop a framework for safe and individualized decision-making when you have unobserved confounders in the data that you're using to train your decision-making process. And the approach we took is take policy learning and calibrate it to some realistic levels of violations of unconfoundedness. Rather than saying unconfoundedness doesn't hold, if that was the case, then if there was no content in the data, right, you could say confounding could be as large as possible, then there's no content in the data, and there's nothing you could do, you can use it for. Okay? So instead we're saying, no, we can bound it, and there could be some limited violations of unconfoundedness. We just have to calibrate our approach to this. The way we did that is just construct this minimax higher regret estimator and minimized it. Okay? So we minimized the worst case policy regret, which led to this guarantee that we'll never do worse than baseline. And then we assessed it in this ischemic stroke treatment case where we showed that if unconfoundedness indeed doesn't hold, then using methods that assume it obviously is very dangerous. You should try to calibrate your policy learning to these violations. Okay, thank you very much.
Thank you for a very exciting talk. One of my favorite works of yours thus far.
Thank you.
Many more to come.
No doubt. Couple questions. I'll start with a simple one. Here it seems like you're using an estimated propensity score within your estimator. Now, as you showed in some of your earlier work,
that's quite dangerous.
That's quite dangerous. How do you deal with that?
So that's a very, very good question, right? So in my earlier work, I was looking at, essentially, if we look at this insight estimator, let me just go back to it. Right, so that's quite dangerous because you're dividing by propensity here. You don't really even know this, so you would have an estimate here. And if the true propensity is 0.1, and you're making errors that's of order 0.05, which would seem like small errors, well, if you have something that should be 1 over 0.1, and instead you're dividing by 1 over 0.05, that's a factor of 2 difference. Okay, so that's really, really dangerous, as David was alluding to, which is exactly why I was looking at using optimal balancing. The reason I think it's less of an issue in this setting is because we're already robustifying this by looking over an uncertainty set of propensities, right? So we're already trying to minimize the worst case over what the propensities could be. So you can think about it as some form of, you can even use this kind of approach if you're trying to be robust to small propensities. You could say, let me optimize this quantity, worst case over errors in propensity. So it's some sort of robust policy learning.
But does it add anything beyond other approaches to deal with that?
You're in unconfoundedness land, and all you're worried about is propensity estimation error, yeah?
Yeah, I mean, so I'm wondering, does it reduce?
It reduces variance. So if you're worried about, right?
I guess the big difference is this ignores sample complexity. Is that right? So even in infinite data, you'd still want to do this because of unconfoundedness.
Yeah, if you were really in unconfoundedness land and you were approaching infinite data, you would want to reduce your uncertainty about E tilde as you got more data. Whereas here, when you have unconfoundedness, that level of uncertainty doesn't go away as you get more data.
I get it. Yeah. So in some sense, they're using a hammer now to deal with the sample complexity issue, but a more fine-grained breakdown of the two could be really important if you want to try to improve the sample complexity.
Yeah.
Right? Because in some settings, you might want to not penalize it because you have enough data to estimate to have confidence in your propensity to score.
Yeah. But if you have confounding, no amount of data can ever identify causal effect. Yeah.
So one question and one suggestion idea.
Okay.
So on the question side, so in the end of the day, you have to select a gamma, right? And I would imagine you would not directly develop the, say you select a gamma, you still would like to do a randomized experiment to make sure, no? I mean, you are more conservative. You try to do much less, almost no harm, but you still have to do a randomized experiment. Am I not correct in that?
I think it's quite safe if you use a big enough gamma, but I do agree that by default, the gamma you should assume if you know nothing is infinity, in which case you say, I do nothing, I'm afraid of intervening.
Of course, but
another thing they're pointing out, which I want to point to is, yeah, maybe you still want to do some experiment in the end to validate this, if you have the resources to do that. But if your observational data did have some confounding, then the policy that you get, even if you did IPW and then tested it, that policy might not just be, it might be a bad policy once you run that RCT, right? So you might end up with a bad policy. So you could get a better policy by choosing a bigger gamma, learning something from data, and running the RCT on that policy rather than the policy that assumes unconfoundedness.
What I'm thinking is select different. I mean, if I'm going to do an RCT anyway, why only to do it with 2 arms? You might want to do multiple.
Absolutely.
To learn on
well,
that.
you need more units.
Yeah.
You have less power.
And on that, in that dimension, I mean, back when a few years back, we had an idea that to randomize gamma, to basically construct robust optimization ideas with random gammas. We have found, not in the medical context, but Natalie worked on it, as you perhaps remember. So that it gave fantastic results, actually, unexpectedly high quality. In other words, still decreasing risk substantially and much better expected value.
Yeah, so
in a way, you're averaging the worst cases.
Put some sort of prior on gamma, like a Bayesian sensitivity.
Yeah, I could even use a uniform prior.
Okay.
So maybe trying that might
that
be.
idea could have a lot of traction, yeah.
Thanks.
Any more questions?
So have you considered using the learned W's as a way of doing introspection to understand which are the patients for whom?
The worst case W's?
Yeah. Because suppose you have side information, like you do chart review on the patients. You can imagine using this to then guide where you do chart review to try to identify the source of hidden confounding, which you could then use to iterate.
Some sort of active learning to say, like, I want to know your propensities more so that I can reduce uncertainty there and maybe get a better policy. Sounds like a great idea.
All right, let's do it.
Does anyone have a question?
Okay.
All right. Then
thank you so much.
Thank you again, Nathan, for his talk.